Physical reality is defined by constant, measurable change. A massive body of ice moves through a valley over decades, displacing millions of tons of rock and altering the landscape with every passing day. Humans have spent centuries attempting to track and predict exactly how chaotic variables like this interact with one another. We see evidence of this tracking in financial markets. Traders monitor thousands of interacting data points, where the price of a single asset depends on the exact second a trade is executed. Looking closely at the historical data stream printed on vintage ticker tape, we see discrete values captured sequentially. Every specific stock symbol is paired with a specific price at a specific moment in time. Underneath the apparent chaos of nature and markets, specific quantities rely on one another. A child's height relies on age. A car's distance relies on speed. An asset's price relies on time. To model this reliance, mathematicians engineered a specific structural tool. We call this tool the function. We cannot calculate the rate at which a system changes until we establish exactly what is changing. We must build a definitive structural model of those relationships first. Stripped of physical context like ice or stock prices, a function is simply a deterministic information processing engine. The mechanism operates on a strict requirement. A specific input enters the system applies a rigid mathematical rule to that input, and a predictable output emerges. We can visualize this mechanism using a simple linear rule. Multiply the incoming number by 2. We begin by feeding an input number, such as 3, into the engine. The engine applies the rule. 3 is multiplied by 2, yielding an output of 6. To test the system's consistency, we feed a 10 into the exact same engine. The rule holds rigid, producing a 20. To utilize this process on paper, mathematicians needed a standardized algebraic notation. That notation is written as y equals f parentheses x close parentheses. Each symbol serves a specific structural purpose. The x represents the raw input. The f represents the established rule of the engine. The y represents the resulting output. We vocalize this formula by saying y equals f of x, or more descriptively, the value of the function at x. This entire system relies on one condition. Every valid input must produce exactly one unique output. If a single input could result in multiple different outputs, the model becomes unpredictable and loses its ability to describe physical events. Mathematical models are not infinite engines that can accept any conceivable data. They possess strict logical and physical boundaries. The complete set of all permissible input values that a system can safely process is called the domain. We can visualize a strict domain limit by changing our rule to a fraction, such as f of x equals 1 divided by x. Standard inputs process smoothly. A 2 passes through to become 1/2. A 5 passes through to become 1/5. But if we attempt to use 0 as an input, the system undergoes a mathematical collapse. Division by 0 is undefined, meaning the number 0 is excluded from this function's domain. Conversely, the complete set of all possible output values that the system is capable of producing is called the range. A rule can also restrict its own outputs. Consider a quadratic rule, f of x equals x squared. If we feed a negative input, such as -2, into the engine, it produces a positive output of 4. Because squaring any real number always yields a positive result, negative numbers are entirely excluded from the range. Identifying a function's domain and range defines the physical boundaries of the scenario it maps. It prevents the mathematics from generating impossible results. When these functions model actual science, such as astrophysics or microbiology, the raw numerical inputs and outputs quickly become too large or small for standard formatting. The distance from Earth to the Sun, for example, is approximately 149,600,000 kilometers. Writing out extensive strings of zeros creates cumbersome, unreadable data. To manage this, mathematicians use scientific notation, structuring the data as a coefficient multiplied by a base of 10 to a specific exponent. By moving the decimal point 8 places to the left, we shrink the coefficient to 1.496, while simultaneously increasing the exponent to 8. The trailing zeros are condensed. This compact notation is easily integrated into a standard function formula describing distance over time. d of t equals 1.496 times 10 to the 8th power plus 30t. This formatting ensures the functional syntax remains readable, scaling from the width of a microscopic cell to the span of a galaxy. By moving away from abstract numerical processing and applying geometry, we can visualize a function's complete behavior. We do this by mapping all of its inputs and outputs simultaneously. This grid is the Cartesian coordinate system, serving as the visual canvas for our mapping. If we plot a series of discrete data points and connect them, they form a straight line, representing the simplest type of rule. We identify this as a linear function. It models constant, unchanging rates, mirroring a physical system like a car moving at a perfectly steady speed. By introducing a squared term to the rule, x squared, we change the geometry of the plot, pulling it into a U-shaped parabola. This is a quadratic function. It serves as the standard mathematical model for curved motion, gravity, and acceleration. If we use a cubed term, x cubed, the graph twists to pass through the origin, creating turning points between negative and positive space. In contrast, the absolute value function snaps into a sharp, rigid V shape. Because absolute value measures pure distance from zero, it ignores negative direction. If we change the rule so that the variable itself becomes the exponent, we generate a curve that starts slow and then shoots upward. This exponential function models compounding interest and explosive population growth. When mathematicians need to reverse this rapid growth, they use the inverse tool, logarithmic functions. Finally, we shift the rule to describe angles. The graph flattens and oscillating into a smooth, repeating sine wave. These are trigonometric functions, the mathematical models for repeating cyclical patterns in nature, from acoustic sound waves to planetary orbits. Every different algebraic rule produces a different geometric shape. This allows scientists to select the specific mathematical curve that matches the specific natural phenomenon they are trying to describe. This map of curves and lines represents our way of tracking how quantities rely on each other. Functions provide the deterministic framework required to link inputs to outputs. These mappings remain bounded by their domains and ranges, keeping the mathematics tethered to logical reality. With these tools, we can successfully map the structural state of an entire system. But once that system is mapped, a more difficult problem arises. How do we measure the exact, instantaneous speed at which that system is changing at one frozen microsecond in time? Basic algebra alone cannot calculate instantaneous change. To answer that question, we must step beyond the function itself. We must introduce limits, derivatives, and integrals. We transition to calculus.